this begs the question, is the operating system a program? Now, this is one of the things that I like to do. What I would like everyone to do, we're going to vote yes or no. Okay? What I'd like for you to do is vote the way it makes sense to you right now. It's not, at this moment, there's no right answer. Once we discuss it, there will be a right answer. Okay? So what I'm trying to do now is sharpen your understanding of, is an operating system a program? So let's ask that question. Is an operating system a program? How many people say yes? How many people say no? Okay, is anybody in the middle? Touchdown, Patriots. Anyway, I'm not a Patriots fan. I'm more of a San Diego. So, those of you that said yes, and that is the correct answer, who wants to tell me, raise your hand, who wants to tell me why they chose yes? Who would like to tell me?
Just like reading in the book how like the operating system starts up, it pretty much just bootstraps itself by loading a different executable and a different executable, building its memory space. So it's like starting its own process. It makes sense to me that it would be a program.
Okay, your intuition is good. You're confusing two different terms in there that we're going to sort out through the day. Okay, so at this point, like I say, you're on the right track, but not quite there. I mean, I'm not trying to say you're wrong or be condescending or anything, but we got to sort it a little bit further apart.
I was just going to say it doesn't exist entirely in memory.
Actually, no. The operating system, when it's compiled and linked, we technically load it all in memory. Okay, and in XV6 it runs all in memory. It doesn't actually get swapped out. So when XV6 is running, it's all in physical memory.
You could say that about.
We can compile and run XV6 on Linux as a program.
We can compile and run XV6
and every
as
other
Linux.
virtually.
And our loader is not exec like it is under Linux. Our loader is called the bootstrap. How many of you have ever heard of bootstrapping a program? Or the bootloader? Okay, that's the loader for the operating system, because exec, which is the loader for user programs, is in the operating system. We have to get the operating system loaded before the operating system can load other things. Okay, we're going to see in a minute that the question about is an operating system a process is a harder question. Much harder question. So, where do processes? Here's what we talk about. A program is out here on disk, then through some mechanism called the loader, it's put into memory so that it can be executed. And once it's loaded in memory and initialized, it is now called a process. Okay? The process itself has more data associated with it than exists on disk. It's called its process context. Okay? And we're going to talk about that as we go along today. So, you might remember, some CS201 sections do not cover process creation, which is done in Chapter 8 of the B&O book, so we don't expect you to know this. But a process is created by the fork system call. That's its job. Okay? And the fork system call has very unusual semantics. First of all, it clones the existing process. It just takes its entire memory region and duplicates it. Okay? Clones it. Those memory regions are not shared. They're private to each process. Each process has its own private address space. We can share things between processes, but that doesn't happen normally, and there's special programming you have to do in order to do that. And since it's a advanced programming thing, we're not going to talk about it in this class. We'll talk about what it means to have shared memory when we talk about virtual memory, but we're not going to talk about how to share memory between processes. Okay. So the fork system call creates a new process. The new process we say is identical to the old process with 2 exceptions. The first one is, because it's a new process, it must have a new process identifier, or PID. Okay. And because they're identical, that is, their instruction pointer is at the exact same line in the program. Okay. We know that there's a different PID. We know that it's there. Okay, because we're outside looking at the whole process. But the code itself doesn't know whether it's the process that originally called fork, which we call the parent process, or it's the one that was created, which we call the child process. So we do that with the return value from fork. Okay? And it's done for very specific reason, and this leads to some of the rules that are used in systems that use the process model. A return value of 0 tells the code that you're now executing in the child process. Okay? And that's by design, that's a requirement of the process model. The reason is that any one process can make a system call to find out what its process ID is. That system call is called getPID. Guess what one of the system calls you're going to add to XV6 is? And it's going to be getPID. Oh no, sorry, it's already there. You're going to add getUID and getGID. Sorry. getPID is already there. Okay. The parent, though, there's no getChild process identifier. The reason is the parent, any one parent can have many children. But any child process can have one and only one parent. Okay. The only exception to that is the init process, which is the first process that is created. And we'll get that when we talk about process creation. And because it's the very first one, its parent is null. That's how we know it's at the top of the tree. Remember tree data structures? You knew you were at the top of the tree when the parent pointer was null, didn't you? So we're using a singly rooted tree for our process hierarchy. All right. So what we're going to have now, as we see here, is we're going to have the parent's going to call fork. Then, when it returns, they're both identical copies of each other except for those 2 values. And they're both executing at the same line of code. They don't start up in main. They start right where you made that call. That is, it's now checking, it's now assigning, in this example, the local variable PID. It's assigning it the return value from fork. And now we can determine whether the parent or the child. Okay? So they're almost identical. And we're executing on assigning PID. So now, if we're in the parent process, the PID now is going to be the PID of the child process. Remember before I said if you're the child, the PID is equal to 0. But the parent may need to know the PID of the child. So fork will tell you, I just created this child, here's its PID. So PIDs are PIDs are positive numbers. That is, they're non-negative and they're not 0. They can't be 0 because of how fork works. Okay? Does that make sense? Right, so we think of them as an unsigned int.
Wait, you said they can't be 0, but we checked for if the PID is equal to 0.
What happens is if you're from fork, it's return value now. It either returns the PID of the child, that's what it returns to the parent, or it returns the value 0. Okay, this variable, we just happen to name it PID. That's just the standard idiom in doing this type of C programming. But you could have called it something else. You could have called it return value.
Okay.
Okay, it's just the name of a variable here. And usually it is because if we're in the parent, then we'll have the PID of the child.
Can a child in turn be a parent?
Yes, that's an important part. Thank you for bringing that up. A child could call fork, couldn't it?
Yeah.
Remember, it's a hierarchical tree. If you're an interior node of the tree, you have both a parent and a child, don't you? At least one child. If you're a leaf node, you have a parent but no children. Okay, does that make sense? Okay, but that's important, and I thank you for bringing that up. I forgot to mention it. It's really critical that it's the relationship of where you are and your relationship to other processes. Not every process is your parent. Only one process is your parent. Not every process is your child. Only the ones that you've created with fork. Okay? It's kind of subtle. We have some code we'll see in just a little bit. So now, if the PID is not equal to 0, we know we're in the parent. And this is a standard idiom. We do fork, and then we check the return value, and we say, if you're in the child, go off and do something. If you're in the parent, go off and do something. Okay? Note that if these just both execute some code and then continue and fall out of the block, they'll both execute the code that comes after. But many times what we're looking to do with the child process is run another program. And this is how the shell works. Okay, so if process 22 was the shell, and you typed ls, you don't want the shell to continue running. You want ls to run, don't you? But the first thing the shell has to do is call fork. Okay? And then here, in the child process, it'll call exec, some version of exec. In XV6, we only have exec, spelled that way. There are other forms of exec. You do man space 2 space exec. On Linux, you can see all the various forms in all their gory detail. Okay? Exec is an interesting system call. Okay? Does anyone program with exec? All right, exec is a very, very strange system call. It's called once and it never returns.
Not even when finished running its
Nope.
program?
It only returns on error. So if it's able to load that program you told it to run, well, when it loads it, it takes the code segment and the heap state segment and the code data and stack segments and overwrites them from the new executable file. So all of your code, including that exec call, is gone now out of memory. You can't come back to it. Isn't that weird?
So it doesn't expect to return?
You don't expect it to return. It should, if it returns, it's because it wasn't able to load and execute that new program.
Does this cause any problems that need to be dealt with? Like
we
you
can,
run too
we
many
can deal with
processes?
them, but we have to know about this issue. We have to know about it. Okay? We have to know that exec will only ever return. You will only ever get to the line of code after exec if the exec call failed. Which means when we call the exec code, we typically don't check the return value. Because if it fails, it has to be an error. So usually in the code, you'll see someone who's written exec, and the very next line of code just prints an error message. And if we think that exec will eventually return back to our original process, that seems like stupid programming style, doesn't it? It seems like it's wrong and it's buggy. But it's not. Okay? So fork and exec are two very strange system calls. Fork is called once but returns twice. Exec is called once but never returns. Fork can return, by the way, an error message. Not an error message. An error which would be number less than 0. And the reason for that is there could be running out of memory or something like that. So if a fork returns an error, the child process was not created, and it's the parent's job to handle that. Okay. The CS201 book has a particularly good example in it, and like I said, there's a copy on reserve in the library if you want. If I get really ambitious and remember, I'll when I get home, I'll be happy to scan it on my scanner and then put it up on D2L or something like that if you guys want me to. We can just talk about it on the Slack channel. Okay. So, we're going off to the child now, and we're going to call exec. In this example, we're going to run ls. So now, the only thing in this process is all the information, all the code segment, the data segment, and the stack segment for ls. But remember how I said a process were those three segments plus other data, which we're getting ready to talk about? The other data is inherited from the parent. That's why we clone it. The open files, things like that. Okay, current working directory. It would be terrible if we typed ls and we create the ls process, they didn't know what directory to do ls on. So we inherit that from the parent. It's called the current working directory, or CWD.
Does exec usually take an argument? So you know
Oh yes, it takes arguments. Fork takes no arguments. Exec has a bunch of arguments. I've got an example that I give to my CS201 class that we're going to take a look at in a minute. And I'll show you how that's done. There's really, usually we do some, you guys remember pointer diagrams? Remember them fondly? Well, I'm not going to draw a pointer diagram for you, but now, sometimes the parent process needs to wait around for the child process to exit. You notice how in Linux, when you type ls, the shell, which launched this other process, those processes are independent. But the shell does not print the $ prompt again until ls is done. That prompt is printed by the shell, not ls. So there's a coordination going on between those two processes. And a parent can sit around waiting for a child process to exit using the wait system call. And wait, and there's several versions of it. Wait system call is used to determine when a child process exits. Okay, if we're in a shell, we almost always want to know about that. Okay, so we can print the new prompt. Depending upon your program that you're writing, you may or may not want to do that. Okay, there's many different reasons for doing it. But that's what the wait system call is for. Wait system call, it does take arguments. See, wait system call in XV6, does it take an argument? No, the wait system call in XV6 does not take an argument. All right, and that's just because they simplified the operating system. And we'll see that because they changed the exit system call.
You said it was for when the child process exits?
Yes, so what's going to happen now over here, see the parent where it's sitting there on wait?
As I understand it, it's no child process was created because PID was not equal to 0. You go to else.
Right, and that's the one on the right.
Okay.
See, that's PID 24. Okay, the return value from fork in the parent is the PID of the child.
Okay.
And so the process whose PID is 22 on the left is the parent because its value was non-zero when it came back from the fork system call. In the, let's roll this back up a little bit. In the child process, it's going to execute exec because its return value from fork was set equal to 0.
Okay.
Okay?
But not wait.
Wait's an interesting one. Wait's job is to just wait, or block, we call it, until a child process exits. There's some details about it. We're not going to worry about them for right now. But later on in the term, you're going to modify the wait, how wait is implemented inside of the operating system, so you will see all that code. It's actually in the file proc.c. Okay? So when ls finishes running, then the wait routine will return. Wait returns a return value, and we typically use it. Okay? This is just a simplified example.